Okay, guys, we'll get going. It's 8 o'clock. We're going to cover some motor troubleshooting. We're going to go over some of the basic or some of the older, more or less energy efficient fan motors that we see out there in the field. And we'll talk to them. I'll open up for a couple questions if we have them, and then we'll open up as always at the end and talk about anything you guys have questions on that we cover in this class. This is a two-part class. We're going to cover kind of the older motors today and just the basic kind of winding setups that you have and the basic components of a motor. And then we'll go into some more of the energy efficient motors on another class on a part two of fan motors. Motor basics. So in every motor, you're going to have your windings and your stator. And those are kind of the magnetics and and then you're going to have your rotor. And that's the part that spins inside and the part that the shaft's attached to on the motor. So the stator always stays stationary. This is what it looks like kind of on a diagram. And you got your power connections going and they actually energize those windings, which causes the bimetals that are attached to the windings to magnetize at a high rate. And because you're using AC alternating current, it's going to switch poles very rapidly through that cycle, which causes that motor to turn, or sorry, that rotor. So your stator is your stationary part of your motor, and your rotor is the part that rotates. If you ever you ever hear the term a flat spot in the windings or the brushes are worn, we'll talk about that a little bit more, but that's usually when you get slippage in your motor or your motor starts to lock up or stay stationary and it goes bad. When the stator is energized, the rotor will make a half turn with each half of a current cycle. So remember, when you're dealing with AC voltage alternating current, if you ever look at a sine wave, it goes from positive to negative, and that's a cycle. That's what they're talking about. Half that cycle. That everything in the United States is 60 hertz. So 60 cycles per second. Is what 60 hertz is. So that current's moving very rapidly per second through that conductor. So as it energizes the stator, it causes the rotor because it's to start to spin, because opposites push off of each other when it's a magnetic field. And so that's what you see, is that's what causes that motor to spin. So then the alternating current changes that half cycle. So remember, you're talking 60 full cycles per second. So this is happening extremely rapidly inside of the motor, these cycle changes. So the alternating current now changes direction. And then the stator continues to repel. Which causes it. So usually you have to bump the motor a certain direction or the brushes on the actual rotor. So if you ever pull out a C-frame motor, this is the easiest way to see this. If you guys look at the rotor, you'll see a bunch of little nicks on the rotor. And if you pulled up apart the inside, you would see those same nicks on the stator. That is what those little cuts inside of the motor are what determine the direction, unless you're dealing with a reversed rotation. But usually, like on your C frames and some of your other ones where you can flip the shaft to get your direction, or I'm sorry, your rotor, that's what that's all about. So if you see those little nicks on the side, that's what we're talking about, where you see those flat spot in the rotor, in the stator, or you see a worn out rotor. So motors over time take a little bit of wear and tear on the inside. Remember, these things are moving rapidly with this magnetic field, and so they will wear down. Most of the times what's taking your motors out, though, is your bearing, either your sleeve or your ball bearings inside that motor are getting warm. They start to go out. They start to make it very difficult for the motor to spin, and then it locks up. But a lot of times you'll get internal damage. Usually when you're taking out the windings or something, you've had an electrical problem. You low voltage, high voltage, you've overheated the windings, and so that'll cause an electrical failure. All motors need a phase shift to start. So This is where we're going to get into the different types of motors and how they get that phase shift to start and how they determine the direction in which they're going to kick on that phase shift. And depending on how the motor's built, it is always going to want to rotate starting one way. So you guys have seen it where, you know, you got a condenser fan and it kicks on and starts running the wrong way. Well, that's because that's where the rotor or the stator has become worn and it doesn't really have an idea of which way to turn. And so that's where you have those internal kind of magnetic contact area where it's worn out. And so when it kicks the wrong way. So that's why you can stop it and hand spin it the right way and it'll take off. If you have to do that, it's time to change the motor. Don't just say, oh, it's spinning now and we're good to go. Let's wrap it up. So make sure that you replace that motor at that point. So equal or opposite attraction, it starts to kick it. So a magnetic field is formed in a slightly different angle. So this is where you're going to have either a pole or a set of start windings, or if you're dealing with three-phase, that's why you can switch the phases and you can actually switch the rotation of the motor on a three-phase motor just by switching the phases. But any way you look at it, you always have to have a slightly different angled pole to kick that motor in a certain direction. So that's how they're all internally built. So we're going to talk about it. So shaded pole, we still see a lot of shaded pole motors. It's going to be your 5411s, your cannonball motors. It's going to be a lot of your condenser fan motors, the ones that without the capacitor. So it's going to be your skeleton motor or C-frame motor. So if you guys can see my cursor, you know, you got your pretty typical, you know, larger condenser fan motor. You've got your 5411 cannonball motor. You got your C-frame here, and then this is just another type of condenser or evaporator, depending on, that's like your 35 to 50 watt condenser fan motor that we see in some of the bigger condensing units. This is something that we'll see like a BB700, skeleton motor. That's that Acme kit. This is showing a Dayton. The nice thing about these skeleton motors is you can actually take the bolts out a lot of times, flip the shaft around to switch the rotation. So if you run into a jam, so you can move that shaft either way just by flipping that whole shaft assembly around and changing the direction of the rotor. Any questions? So real quick, guys. Sorry. Shaded pole motors have copper bands on each pole. So those copper bands that copper band gets magnetized from the electrical current. That's where you get that shaded pole. It's on one side of the windings or it's offset, and so it throws the rotor in a specific direction, and that's what causes your rotation. So shaded pole motors typically have the following characteristics: they got a low starting torque, they got a low efficiency, and low cost. That's why usually you're only using these with a very thin fan blade on them. They're not meant to spin big blower wheels or squirrel cages. They can't do a lot of load. They don't have a lot of starting torque. So, and if you do put a heavy load on there, it's going to take a little bit for that motor to get going. So this is where you're going to be like case fan blades or condenser fan motors. And if you guys are familiar in the field, you're looking at those going, yeah, I deal with those every day, all day. So pretty typical motor we use in the trade. So again, you just got your common and your ground. And if you have a multi-speed, just make sure that you hook that up right. So split phase. So this is another really common motor we use. This is going to be a lot of your, this is going to have the set of start windings and the set run windings. So there's no difference when you pull the cap off. You'll see the two sets of windings inside of there. But it's going to energize the start windings. Usually a centrifugal switch takes out the start windings. So what it does is it energizes the start windings. As soon as that motor starts cranking up to a certain speed, there's what's called the centrifugal switch in there. As soon as the speed hits that centrifugal switch, the switch opens, de-energizes the start windings, and the start windings stay out of play until the motor slows down to a speed to where it re-engages the centrifugal switch. Here's this. If you took the bell end off of a split phase motor, this is what you would see. You would see almost layered offset windings. And so obviously, because like we talked about in that a couple slides ago, you have that offset set of magnetic windings that kick that motor. That's going to be your start winding. So here's a diagram to kind of better illustrate what I was just talking about. So you got that centrifugal split for a split phase motor. You're gonna, when that motor energizes through the contactor or the call for that motor, the mechanical switch is used to de-energize the start winding. After the motor starts, the centrifugal force of the motor spinning opens the switch, and the start winding circuit remains open as long as the motor is running. Do we have any questions on shaded pole or centrifugal motors? Does it make sense, guys? How we're kicking those and starting those and how we're determining direction? Perfect. So PSC motors, so permanent split capacitor motors. You guys, again, we deal with these a lot. Condenser fan motors. A permanent split capacitor is going to have that run cap in play. So, you know, where you guys have motors, you got your 3 leads or you have multiple leads. You might have directional leads, like where you have the spades on the bottom of the motor where you can switch it clockwise or counterclockwise. So you're usually going to have 4 leads for your rotation. And then you're going to have, you know, up to 3 speeds and a common for your motor. And then you're going to have those 2 brown wires coming out for your capacitor. So indoor blower motors, condenser fan motors is where we see most of these. So permanent split capacitor motors, PSC motors, they're probably, if not the most common, the second most common motors. If you are an HVAC tech, it'd probably be your most common motor. We still see a lot of shaded pole. And then, you know, ECM motors are taking the place of, or EC motors are taking the place of a lot of the shaded pole stuff. That's where we're getting that high energy of deficiency, and because of the low starting torque, we're able to do that. So it has a little bit more starting torque. This permanent split capacitor has a little bit more starting torque than a shaded pole most of the time, but you're still dealing with, there's not a whole lot of load you can throw on there. So a run capacitor is permanently wired into the start winding circuit. This capacitor provides a partial voltage to the start winding. So it has a low starting torque, it's a low to medium cost, and it's a medium efficiency. So again, guys, depending on the speed you want to run it on your indoor blower, you could have, you can energize these at different times too. You could hook up all 3 of those to different lines, depending on if it's a call for heat or a call for cooling. Cooling is going to usually run on high speed, and depending on the heat package, you might run it to medium or low speed, you know, just to give time for that heat exchanger to warm up. So you might have a couple of these terminals hooked up. The only thing I would tell you is don't energize 2 of the speeds at the same time. So you're going to hook up your high and possibly your medium speed. If you're dealing with a blower motor or your application, you're going to have your common line coming in. If it's 230, that could be the other side of your 230 or 208. If it's a 115, that's going to be your neutral. And then you're going to have your 2 brown wires coming out that go to your run capacitor. And then you're going to have your ground. So, and then if you're dealing with a directional where you can change them, you're going to have 4 more leads come out, like what you see in this picture right here. So you got the yellow block there, kind of shows you the 4 leads for changing the rotation of the motor. You've got you know your line voltage leads where you're going to hook up your common and either your low, medium, or high speed, and then you've got your 2 brown wires that are for your capacitor, your run cap. So difference between looking at a run cap and a start cap, guys, for you don't know, run caps usually have low microfarads. Start caps usually have high microfarads. Start caps are usually brought in play for a fraction of a second for the kick, and then they're used, a relay or something used to drop out that start capacitor out of the circuit. So, and keep the run in play. Make sense? Any questions? Okay. Talk about 3-phase motors. So 3-phase motors is when you're getting into, it's got a lot bigger loads. So if you're pushing some pretty lofty loads, 3-phase is the only way to go. A 3-phase motor has start windings and has a 3-phase motor has start windings or capacitors needed. The motor has the following characteristics. This should say no start windings or capacitor. So there should be a no in there. So this, because you're using 3-phase power, you're already getting, you know, phase changes through the different windings because you're dealing with 3-phase power instead of single-phase power. You're not looking for a phase change to happen on the same circuit. You actually have two phase changes happening through the 3 leads there. Make sense? So that's why we don't need capacitors on three-phase motors. So they have a really high starting torque, they're high efficiency, and they're medium to high cost. You know, anytime you're getting into three-phase motors, because they are high efficiency and because of the way that they're wound and stuff, they usually are pretty costly, but they're my preferred application. And anytime we can use a three-phase motor, we're going to get a little bit of freedom. We're going to have less component failure. You know, and as long as we get good voltage to that motor and we take care of the bearings, if there's grease zerks on the motor or whatever, that motor is going to last a long time. Also, the nice thing about a lot of these three-phase motors is these larger ones. So what we're looking at right here is this is you see that top one where it's kind of has the back shroud and then it's got the ribbed body. That's an air-cooled motor. So it's got a fan blade on the back there that actually cools that motor as the rotor turns. So as that rotor spins, it spins that fan blade on the back, and then that fan blade actually cools that motor through that shroud. It pulls in through the backside of the motor and cools the body of the motor. So, and this other one is where you see the holes actually in the motor itself. It's actually drawing air through the motor to cool the windings. It's an open windings. So this one's an enclosed and that one's an open. So, any questions on that? Man, perfect. We all know about motors, so I'm just wasting my time here. So three-phase motor delta connections.
Not wasting your time.
I'm just kidding. So I know there's a little bit of goodness we can get out of all this. I mean, even just brushing up on this morning for me was a good refresher on what we're looking at. So obviously, guys, if you're looking at this wiring diagram, you want to look at whenever I was on the phone a couple times yesterday with a few techs, and you know, when you're dealing with three-phase, we're talking about checking the combinations. And so this is what we're talking about. When you get your black and your red test leads out, the best way to check a three-phase motor is to go L1 to L3, look for your potential voltage there. Could be 208, could be 230. Make sure you look at the data tag on the motor. Could be it's always going to be 208 or 230, even if the motor's 460. You might have a 277 high leg in some of the old Delta Ys. So, if you do have a high leg, please get on, and you haven't dealt a lot with that type of application, please get on the phone with your senior technician and talk through that situation. So we had a guy hook up a pigtail a couple years ago to a high leg and blow his sawzall right out of his hand. So just be careful when you're dealing with a high leg. If you test across any of the combinations, L1, L3, 240. If you go L1 to L2, you should get 240. If you go to L2 and L3, 240. You need to check all three of your combinations anytime you're dealing with a three-phase troubleshooting application. So, because it's going to tell you certain things. Usually on these motors, if you're throwing an amp clamp around the leads when the motor's running, you should get common amps across a three-phase motor. So every leg should, if you're pulling 3.2 amps on L1, you should pull 3.2 on L2 and 3.2 on L3. It should be really close. So if that's how you know you're doing fine. Usually if you're using depending on the compressor on a single phase, the start windings and the run windings will have each a value. And if you add them together, when you're checking your amp draws, you'll get different, or if you're checking ohms between your start runnings in common and your run windings in common, and then your start runnings windings to run windings, the two should add up to what the value of each individual set of windings. So a little bit of troubleshooting there. If you guys test these and you have good voltage there sending from your contactor, but the motor's still not running, you're going to want to disconnect those leads from the motor, and you're going to want to ohm out the motor. So has anybody used a mega ohm meter? Okay.
CNM hasn't used it.
Okay. I would suggest you guys, if you're dealing with a lot of three-phase motors, carrying a mega ohm meter can save you a lot of time. If you're having a nuisance trip or you're having a problem, what a mega ohm meter does is it looks for that finite disruption inside of those windings. So usually those windings are pretty robust in these bigger motors. A mega ohm meter kind of sends a signal through there, and it looks for good resistance through those windings. And so, or continuity, it looks for good continuity through those windings. And so, mega ohm meters, you can get a fairly inexpensive one. They can get really expensive if you're doing a lot of like calibration and testing. But for what we use in the field, I carry a mega ohm meter. I've used it multiple times. When I go out on like third or fourth calls where guys can't figure out what the heck is tripping the breaker, and 9 times out of 10, there's something going on in the windings that we can't catch, but it shows up on the megometer. So if you guys are dealing with a nuisance trip, or if you're dealing with a motor dropping out sporadically and you don't know why, and it's causing like a high head pressure trip or something, and you can't put your finger on it, the best thing to do is, see if somebody in your crew has a megometer, or get one yourself, take it down there, disconnect the leads, and then hook up the megometer and run your tests. So let's talk about the synchronous or nominal speed of a motor is determined by the number of poles. The more poles, the slower the speed. So this is how you get your RPMs in a motor, guys. So one cycle has 2 current flow reversals. 60 cycles has 120 flow reversals. So like we said, 60 cycles, it's from top to bottom, positive to negative. And so you have 120 changes in there to spin that rotor. So speed, cycles times reversals divided by poles. So example, you calculate the speed of this first cycle, and we're always using 60 hertz. If you have 2 poles in that motor, then you're going to do 60 times 120 divided by the 2 poles, and you're going to get 3,600 RPMs. So this is what I was talking about at the beginning, slippage. Slippage is where a loss of speed from the motor load. For example, speed may be calculated at 3,600, but actual performance is 3,500. So you could have a heavy load on that, and so you might get some slippage. It might not be cranking like it would if it's freewheeling. The motor speed calibration tools are quite expensive. I know of 2 guys in the company that have them, and we've used them a couple times, but it's not necessarily necessary. But if you think you need that, if you think you have a motor with a tremendous amount of slippage, then let us know. We can help out with that, or when in doubt, like get it rebuilt or change it out. So if it's causing sporadic problems because the slippage is quite a bit and the motor's fairly old, then you're probably going to end up just changing that motor. So biggest thing that I want you guys to learn from these classes is, like, let's try to use the same terminology. If there's terminology that we're not currently using right now, we're trying to use it when we're on the phone tech supporting with the guys. We want the guys to kind of learn the proper terminology, because the best part of this is, like, when you're talking to a motor manufacturer or a motor rebuilding company, or your local motor shop in town, these are the terminology they use every day. And so when you're trying to talk to them on the phone about what you got going on, or you're trying to troubleshoot it, the terminology is super important to understand what you're talking about. So motor mounts, you got your cradle mount. So again, we see these all the time. Not my favorite. Usually those cradle mounts get loose, the motor comes off or wears out. That little rubber sleeve, starts to wear down, and then the motor starts bouncing all over the place and wreaks havoc on whatever fan blade or blower wheels on the end of it. The rigid mount's my personal favorite. Obviously, it's robust. It's usually on your larger motors, and it's able to handle the whatever vibrations or situations it's running into, any harmonics, a lot better than the cradle mount. And the belly band mount, which we've seen a lot of, like condenser fan motors and stuff. The one thing I will tell you guys is, like, understand if you're dealing with a fully enclosed motor or an open motor, understand some of those motors are directional depending on how they oil the bearings. So if you tip them upside down or sideways or downside, you need to understand, like, what direction they need to be sitting, because if you do the wrong thing, the oil will not be up against the bearings. It'll run dry. It'll wipe out the bearings. You'll be back there in a couple of days. A lot of times when troubleshooting condenser fan motors, a lot of guys will go out there and the thing's tripped off on high head pressure. They'll reset everything. The thing will run great. They'll watch it for about a half hour. Everything will be fine. They'll leave. They'll get a call a couple hours later. It's off on head pressure again. What I will tell you is, if everything's running great, stick around for about an hour and touch the side of that motor. If that motor is extremely hot to the touch, bearings are going out and it's going off on internal thermal. So you need to change that motor. So, and I can't tell you how many times a year in the summertime, that one gets, guys. It's probably the most common callback I get on AC calls is that the bearings have gone out in the motor. It runs fine when they start it up. After they reset the high limit, they wash the coils. Everything's fine. It seems good. They see the motor's running fine. They drive away, and then they're back. Them or somebody else is back there within a few hours or the next day with the same situation. So run the motor, touch the motor. If you guys want to know the difference between a warm motor and a hot motor, then touch the motor when it's running. Start touching the sides of your motors when they're running, just to see what the difference is. Log that in your brain. So, and then the stud mount. These are most of our evaporator fan motors are stud mount. So, well, that's a pretty short one, guys. I like it. So is there any questions on motors or troubleshooting motors or situations we ran into that you have questions for me on?
Hey, Jim, one thing I want to add real quick.
Okay.
Is back on the motors, on the bigger motors, is knowing what frame you have a motor to will also help.
Oh yeah, if you're dealing with a 48 or a 52 or a 56, you've got to know your frame for your mounting and your application. So the things that you guys should be looking for on your nomenclature is obviously your voltage, your phase, your rotation, your frame, and then your RPMs. So and your running load amps. So because all that's going to play into the overall system. So, I wouldn't go more than 5% difference, if that, on your RPMs. So if you can't get it within 5% of where your RPMs are, if you're going to an aftermarket motor, don't do it. So it's not worth the troubles. Just get the right motor in there. Does that help, Troy?
Yeah, no, that's great, because I know some of the guys on here may not know that, but that's a good thing as well.
Yeah, whenever you guys are going from, if you're not doing like OEM type parts and you have that universal motor in there, just make sure you check those few things. So, because it'll get you caught every time. And then when you're dealing with multi-speed, you're going to be dealing with multi-amp draws. And if you're dealing with multi-voltage taps, you're going to be dealing with the same thing. So make sure you're lining that up within 5% of what the OEM manufacturer is requiring for that piece of equipment. I've seen a lot of HVAC motors or condenser fan motors where they don't line up the RPMs. They do like 1125 and they're doing like an 825.
Maybe just, oh, you're taking it? Okay. Yeah. Because I just wanted to see if I can get this trailer in there.
Hey, Troy. Troy.
Yes, sir. Yes, sir. Sorry.
Oh, no, you're good. Any other questions? Okay, guys, that was easy. So I appreciate you tuning in. We'll get this up on the website. If you have any other motor questions, make sure you reach out. There'll be a part 2 where we go into ECMs and VFDs and stuff. So that'll be coming up in a week or two. So we'll follow up on more motor discussion because we deal with them so much every day. Have a good day.
Thanks, Jim.
Thanks, guys.
Thank you.